Swayam Prabha. Digital India. Educated India.
Hello everybody, today we have ethers. Okay, so we're going to get high on ethers today. Let's see what we can do with ethers. Ethers are typically used for solvents in a lab. You know, that means they're neutral, they're not reactive, they just help things to mix around. Okay, so what's there to learn about them except their solvents? Well, there's a little bit more. Let's look at it. So an ether is an oxygen that's connected to two carbons. And these carbons should have hydrogens, not carbonyls or oxygen. So you have to have, let's say, primary, secondary, tertiary, whatever. I'm just going to put, you know, IH. That would be the smallest ether out there. And that's a gas. The one that you typically call ether in a lab is an ethyl ether. That's typically what you call ether, okay? But there are, of course, you can change the R groups and you can have millions of ethers. Let's see how you can name them. Typically, we just say what's on the each of these groups. If they're the same, then we say diethyl ether, okay? That's a common name. That's typically what, when we say, oh, put some ether into it or use ether as a solvent, that's what we typically mean, diethyl ether. Okay. Now, pentanes sometimes are also called that way, but these are the actual ethers. All right, let's look at some common ether naming. So here, let's say you have ether with two R groups that are different. Then what we do is we take the longer one as the parent and this as your side chain, and so that's going to be ethyl propyl ether. It's really simple for common naming. But let's say these get really complicated, then we need to go IUPAC naming. The IUPAC naming basically also has to have two sides to the ethers, and so we want to name something like this. So here on this side, this is longer than this. As long as this is shorter than this, that will be your alkoxy, and that's your parent. Okay, so alkoxy is the smaller part. So here this is ethoxy, and here oxygen has an R group, so then that carbon should have the lowest number possible. So we'll start numbering this way, 1, 2, 3, 4, 5, 6. So this is like a side chain. So it's ethoxy, 2-ethoxy hexane. Okay, now you can get more complicated than that. Let's say you have a chain like this, and you have an OCH3, let's say, and then let's say somewhere here you have a hydroxy, a double bond somewhere here. So here you have a lot of stuff here. Now, alcohols have a lot higher priority on the naming. So we learned about the naming priorities, and it doesn't change, you know. Carboxylic acids, actually carbonyl chloride, then carboxylic acids, then esters and so on. And then you have carbonyls, then you have alcohols. So these are higher priority. Then you have alcohols, then you have alkenes, and then you have triple bonds. And here you have OR groups. Okay, and then you'll have, let's say, RX or R alkyl groups. So therefore, you have to number it giving the alcohol lower number because it has higher priority. And also, if you didn't have the alcohol and you had the alkene, you would have to give the alkene the lower number. Okay, in this case, we have an alcohol 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so The 3 here, it's going to be, let's say, counterclockwise, so 3s. And the 9, let's say I do stereochemistry there, let's put some here too. 9 is going to be then clockwise, 9r. And so then let's nail all the stereochemistries and the EZ. This is a trans, and so it's going to be an E. So then that's 5E. And then you can say what all is on there. So here, since alcohol has the highest priority, your suffix would end with the highest priority group. So it will be an ol. And then this is 10 carbons, so it will be a decanol. And well, you have to say where it is. It's 3-decanol or decan-3-ol. But you have to incorporate the ene in the name and say that on 9 you have an alkoxy group. So here you can say 9-methoxy and 5-ene, so dec-5-ene-3-ol. There's no space here, dec-5-ene. And we already specified that it's a 5E, so we don't have to put that again here. 5-ene-3-ol or 5-decene-3-ol. So here's something that you can always, count on for IUPAC naming is the order priority group. All right, let's look at some properties, physical properties. For example, if you replace this with hydrogen, it will be water. So do they look anything like water? Not really. So if you have water here, the only difference is you're putting carbons and it becomes ether and it evaporates really quickly, whereas water is going to be there for a long time just because of that hydrogen bonding. All right. So if I replace one of the hydrogens with an R group, let's say CH3OH, that's an alcohol. And then when we replace 2 of them, they become ether. Okay. Now, so you can see the angle here is about 105. The lone pair repulsion is higher than the bond pair. So the lone pairs expand, and so the amount of space for this is squished. So that's 105 degrees, that angle. When you put a methyl, then it's kind of goes down to 109 in an alcohol, and then 112 here. Okay, so you can see the methyl groups are kind of expanding because there's steric repulsion between these methyl groups. You can also look at the boiling points here. The boiling point here, water is 100 degrees, so all in centigrade. And this one, and methanol boils around 69 degrees, 68 degrees. And then this is about minus 25. Okay, so one OH bond has such a huge effect. All right, I mean almost like a 90-degree difference. So you know how much hydrogen bonding contributes in a molecular attraction. Now, if it's a gas, then obviously it's not going to be useful for us. For it to be useful in lab, what we do is we then increase the London dispersion forces by lengthening this carbon chain. So here you do have a dipole, but because the angle is so wide that the dipole is really very small. Okay, so if you take this and make it into an ethyl group, then your boiling point actually goes up quite a bit. It goes to 35 degrees. So that's quite big, 60-degree difference there between just putting 2 methyl groups. So London forces also are quite significant. You can't just say, oh, it's just a little sticky interaction. Look at the boiling point difference just for adding 2 methyl groups. If you add 2 more methyl groups, guess what? It's 91 degrees. So London dispersion forces they are quite formidable, okay, and a force to be reckoned with, because you can see the boiling point increases a lot just by lengthening the chain, which means they can now stack up a lot more with all the London dispersion forces, just electrons, shifting around. All right, so ethers have no hydrogen bonding, and so low boiling point, but it can increase with alkyl groups. Now, if you compare this with, let's say, so you can see just putting an oxygen makes a huge difference. That's 20 degree, I mean quite a big difference here, 17-degree difference. But then again, when you put R groups, it's going to be a lot more. So ethers have no hydrogen bonding. So what's the point? I mean, if there no attraction to things like water and alcohol, how can we use it as solvents? They can have dipole-dipole attractions between oxygen on the ether and, let's say, alcohol. So let's say I have an alcohol here. This dipole can then attract this hydrogen bonding, dipole hydrogen bonding attraction. So they are very good solvents because they can dissolve things that have hydrogen bonding. They can also dissolve things that have dipole-dipole because like dissolves like. So if you have, let's say, a ketone and you have a delta minus, delta plus, you can still have very similar attractions here. Okay, so therefore ethers, these are polarized very, very slightly, not as much as a carbonyl, but they still, the dipole-dipole attractions still help dissolve things quite a bit. So it's like a universal solvent. For example, the most common solvents out there, as we said before, are ethers. So they're solvents because they're not ionic and they're neutral, and they're very good at doing these intermolecular attractions with dipole-dipole molecules and alcohols, and even to some extent some nonpolar stuff. Have low polarity, unreactive, because OR bonds are quite strong, it's hard to break them. So good solvents, because you want a solvent that's really not going to interfere with the reaction, you just want them to get other different species together to react by dissolving them and making contact. So they're good solvents because they're unreactive. Imagine the solvents reacting with everything, then obviously it's going to really mess up your reaction. Some very common ethers typically used are these oxacyclopentane, tetrahydrofuran is another one, THF. But there's a different kind of ether, but I'm just going to put it here, THF, tetrahydrofuran. The dioxanes are very big industrial scale solvent that they use, and then oxane, just one oxygen. Okay, these are some of the most commonly used industrial solvents. So if you see these on top of your arrow or below your arrow, they're just there to dissolve things and make them get long. All right, so let's see how we can make these ethers. What do we do to make ethers? So let's look at preparation of ethers. How are you going to use the molecules to synthesize ethers? The most common way is to take some alcohol, and diethyl ether is like the most common one out there. So you can take a ethyl alcohol and distill it with just some aqueous acid or some solid acid, like they have HCl, let's say, and you can put that on a column and just run some ethanol on it. This is going to get protonated, the HCl can be ionized, and so now you're going to get AOH that is now, this is a bad leaving group. And you know that because the pKa is 16. Now when you protonate it, well, this bond becomes very weak because This is very electronegative, and it's pulling those electrons and thinning out that bond. So this is really not a good overlap. So it's easy to break that. So the pKa now drops to less than 2. So now it's an excellent, good leaving group. And that's the whole point in protonating these for most of these reactions. That's what you do. Then the same alcohol, when you're running through the column, is going to come back and be the nucleophile. Now here, that's your starting material. Here is going to be a weak nucleophile because it's neutral. So it comes in and kicks out the water. And so now you have the water leaving, and so you have that with an oxygen, and that oxygen has got a hydrogen, so it's protonated. No worries, the nucleophile, weak nucleophile, can also be a weak base, and we saw that in SN1 and E1 reaction. So it's the same kind of chemistry. We're not doing anything new here, so we're taking that hydrogen off with a weak base there. So the same molecule can function as a base and a nucleophile and the starting material all rolled into one. So here is your diethyl ether. Now you can put different R groups and make different ethers. They don't have to be symmetrical. You probably get a mixture if you don't have it symmetrical. All right, so now what's another way that we can make ethers? The Williamson, which is like the most common way of making ether. So let's say I have a big ether that I want to make. Let's make MTBE, which used to be a methyl tert-butyl ether, which used to be an additive for gasolines. Methyl tert-butyl ether. So California banned this probably in the 90s because even though this is a really good additive, it does increase the octane number, so it burns more smoothly, and it increases the oxygen content for combustion and so on. It still leaches into the groundwater, and so it became a pollutant. So now they've replaced the MTBE in gasolines with ethanol, which also has oxygen, and it can also increase the octane level, not as much as MTBE, but to a reasonable extent, without killing people and animals. So that's a gas. So let's see how we can make this. So if you cut it in two, we can either use the methyl or the tert-butyl group. Let's look at which one it is. So the main overall method is to take ROH and take off that hydrogen. It's slightly acidic. You can put sodium hydride. You can even put sodium hydroxide, but that's going to be the same pKa about. So this is going to be, sodium. Let's use sodium hydride. And you can make an alk oxide, and that's typically how alk oxides are made. Because hydrogen's a gas, you just blow it off. And then this alkoxide can do a backside attack on an alkane and make an ether. So you bring another group with a good leaving group like a chlorine or a bromine or even an iodine, and then you can kick that out. And so now you would get an ether. Okay, so my question is, which one do you want to bring in with the leaving group? Do you want to bring in the methyl with the X group or T-butyl group with the X group? Which one do you think would be better for this reaction? Hint, hint, this is an SN2. I guess I kind of gave that away because primary or methyl would be a lot better for SN2 than T-butyl. There won't be any SN2 here. So you want to bring this with the leaving group. So if you want to make MTBE, you would take a T-butanol, which you can get, in a can, and then you can put some sodium hydride into that, sodium hydride into this. This is just a base that's going to take off that hydrogen and give you an alkoxide, O minus. So here you have Na plus, and you have your hydrogen leaving. And now you're going to use this with the methyl with the X group for a leaving group. That way you will have a nice backside attack. So you'll bring in your methyl group and bam, hit it from the rear. This is methyl bromide or methyl chloride. And then you can take this and do a really nice backside attack here. This is perfect for SN2. You can't get better conditions than a methyl. And you made your ether right there. I think there are some states that still use MTBE, so I'm pretty sure this is still in production. Sodium bromide falls off, and so you can just distill this, and so you'll have a still going constantly. All right, so we'd also learned of other ways of making this. We did couple of reactions with alcohols, with alkenes. Let's say you have this. We said if you put H2SO4 and water, it's going to add water. But if you put H2SO4 and alcohol, then you're going to add the OR group. And here, it's acid and alkene. You know the mechanism already. It's going to be Markovnikov. That's right. So here, you're going to protonate this, and then you are going to protonate it on the carbon that has more hydrogens. That's Markovnikov's rule. And so now you have a hole here, and your alcohol is going to hit that, and then it gets deprotonated. And I'm not going to draw that because we've done this like 100 times, so you already know it, the mechanisms I'm using. So here's your alcohol goes HOR, and that's how you make ether. Now here, in this case, you won't have any rearrangements, but you know, in some other cases you could have rearrangements. If you don't want rearrangements, then we use the same thing. Let's say you could use this, and I don't want any rearrangements. I'm pretty sure you remember this. We put mercuric acetate and we put water. So instead of water, what we're going to do is we are going to put an alcohol. So that way, instead of attacking with H2O, you attack with ROH. So you have an OR group that tags along. R group's not a leaving group. The hydrogen will leave and you'll get an OR right on top. So you're not going to get any rearrangement. You're just going to have, well, let's see, AgOAC, and this is going to attack it in the most substituted position. And so it is Markovnikov, but here you might get rearrangement in this method, but here you don't, and that's the whole purpose of that. So here's your OR group, and then I'm going to put 2 arrows. You're attacking, then you deprotonate with another alcohol, and then your AgOAC is there just hanging by the thread there. Then you can get rid of it with sodium borohydride, and that's something that you have done before. So here's another way to make ethers, a really nice way, clean way, with no mixtures. Now, what can we do? I mean, what kind of reactions can we do with these ethers? Are they good for anything in the lab? Well, we do have a way to take ethers and splice them in two and get back the alcohol if you really want to. But this is more of a reaction to show you that, look, you don't want to use very strong acids with ethers because they can actually hydrolyze them, okay? There's also another way to make it with epoxide, but we will talk about that in a minute. So I'm not going to put epoxides here because you can open up epoxides with alcohols and get ethers as well. So here's a reaction that we can do, and as I said, the reason why we are using that as a solvent is because it's unreactive, okay? So this is just to show you, don't use ethers with strong acids and gonna boil them because they can chew up the ethers and react with them. Let's say you have a strong acid like hydroiodic acid, then you're going to protonate that, and you are going to then have a good leaving group. A bad leaving group turn good leaving group. Then that means it's going to be reactive. So here you'll put a hydrogen here, and now this is going to be attacked by the iodide. So here an iodide can come in. Obviously iodide cannot attack here for an SN2 because this has a p orbital, pi bond, and there's no SN2 there. It can only attack here. And so this anisole, which is in anice, can get hydrolyzed, and you can get phenol and methyl iodide. So you will only do this if you actually wanted to get phenol from anisole. All right, so as I said before, ethers are not very reactive, so it's to your advantage that we don't have a long list of reactions for you to learn on ethers. It's just an ROR can be hydrolyzed with acids, HX to ROH, and let's say RX. That's pretty much the story here for the reactions. But we have some ways to prepare them, and we also know that ethers have some very, very stable, unreactive, neutral properties that make them good solvents. See you next time. Bye.